So let's see. I don't see the recording light.
It's recording.
Good. All right, so let's see. This one's going on YouTube, so you all should be anonymous and invisible and muted. Use the chat function to communicate, to ask questions. And you can all hear me, apparently. Well, I told you to mute yourselves and then I ask a question, so that's stupid. All right, so I think we're up to discussing Fourier transforms. Let me ask though, is there any interest in my saying a few words about Lebesgue integration? So can somebody send me a signal on chat about that? I'm going to grab a coffee here. Well, it's not made yet. Let me, in the absence of a question there, let's just imagine that we have an interval, say A to B, on the real line, and we have a function that might look like that, and all of its points then lie in some sort of an interval here. And the idea of Lebesgue integration is to divide this y-axis into smaller and smaller intervals. So intervals like this. And then take the limit as you have large numbers or infinite numbers of intervals there. And then what you do is you say, well, let's see, something is popping. I don't know what that is. Anyway, so this is some function f of x, and we're going to define the integral. I don't know why that stopped working there. Integral from a to b of f of x dx is then going to be a sum of f of, let us say, xk times the measure of what we can call jk. So in other words, here we see that these points here fall into this first interval, J1. And we can say, well, what is the measure of the points down here that whose F's fell into this interval? That's the measure of this set. And so we multiply that measure by, there's something, apparently my sound, I just wonder if you've got some sort of feedback loop here. Anyway, what we do here is we multiply the measure of this set here. So that's m of J1, which is a certain distance effectively on the x-axis, times the function evaluated at an arbitrary point inside this interval. And we just sum over them. I don't know why this, somehow this pen keeps failing me. Okay, we do that sum. Now, what I haven't told you so far is what we mean by measure. And so what we do is we have some set of points on the real line, say. And then what we do is we take, we create some intervals that include all the points. Like that. And then we sum up the lengths of these intervals, and that gives an estimate of the measure. But it's clearly an overestimate because there are spaces between those points. And so what you do is you add more and more, you break these things up like that. And like this. And so forth. You keep breaking them up into finer and finer meshes, and until the total length, sum of the lengths, reaches some minimum. It's a greatest lower bound, and that's an estimate of the measure. But what you do as a check on that is you say, well, what about the points that are in the interval from A to B, but aren't these points? Well, you then compute, you do the same thing for those points. So for example, we do this, I'm forming some intervals, subintervals that contain the points that aren't in the original set, say S. And so then you continue in this way, and you get an estimate of the length occupied by points not in the set S, and an estimate of the lengths of the intervals of the points in the set S. And you can consider this to be the measure of an estimate of the measure of the set S, and this to be a measure, sorry, this was, let's see, let me erase that. This to be a measure of the complement of the set S. So the set S is there, the set S prime is here, it's the points not there. And the set S is measurable if M of S plus M of S prime is B minus A, the total length of the interval. So that's the definition of measurable. And then what you do, as I said, for a function is you divide up the range of the function into subintervals, and then you ask what is the measure of the set of points on the x-axis that went into each of these subintervals. And so then you say the integral is the value of the function at arbitrary points in each of these sets down here, and so forth, multiplied by the measure of the set times the function at a point in the set. And that then is an estimate of the Lebesgue integral, and then you take the limit as you impose a finer and finer mesh here in the y-axis, and so these sets, these J sets, become more numerous and much smaller on the x-axis, and you take the limit of that. Anyway, that's defined to be the Lebesgue integral, and it is in some sense, you can think of it as a more natural definition of integration, and mathematicians have used it to prove various things, and in particular, this is relevant to Fourier transforms. So let me now go to Fourier transforms, and Uh, Here, let me just get a little more water here. Okay, so let's go back to the beginning of this chapter. And think about Fourier transforms. First of all, the complex exponentials that we used in Fourier series are orthonormal, but they're periodic. And if you want to represent functions that are not periodic, then well, you need something else. And the most useful thing has turned out to be the same complex exponentials, but where the factor multiplying x is not 2 pi n over L, but just an arbitrary real number. And when you can even have complex k, but we're not going to do that, at least not until the very end of the chapter, and I'll probably skip that. Actually, no, I'm not going to skip it because Laplace transforms are irrelevant. So, as you know, the interval from minus L over 2 to L over 2 is arbitrary in the Fourier series pair, where the function's expanded in as its Fourier series and the Fourier coefficients are given this way. The question then is, what happens if you let L go to infinity? And what happens is that this pair becomes effectively a Fourier transform and the inverse Fourier transform. And the first thing to do is to use the nearest integer function. And let me say what that is in case some of you don't know about it. And in fact, it's probably something that's more used in computer science than in physics. So the nearest integer, let's see, the nearest integer function of an integer n is simply n. The nearest integer function of n plus epsilon is equal to n if epsilon, the absolute value of epsilon, is less than 1. And so that's basically the nearest integer function. In other words, it's the nearest integer function of x is the integer closest to x. So that's basically the nearest integer function, and I don't think there's anything more to say about it. So we're going to use it, and what we're going to do is we're going to use it to start from this formula, this Fourier series for the function f of x, and convert this integer n into a continuous variable y. But if we instead say that what we mean is the nearest integer to y, then what we can say, we can define a function f hat of y, and that function f hat of y will be f sub n when y is close to n. That is to say, when y minus n is, actually I say here y minus n is less than a half, and I can see that in over here, I should have said for epsilon less than a half. So let me correct that. In other words, if epsilon is, let us say, in other words, here, let's just check this. Suppose we have the nearest integer 5 plus 0.75. Well, this is almost 6, so this is 6. And on the other hand, 5 minus 0.75 again, well, this is going to be the nearest integer to 4 and a quarter, and that's just equal to 4. So I was too fast a few minutes ago with the top equation. So instead, what we have is that if f hat of y is f sub nearest integer to y, then f hat of y is going to be f sub n when y minus n is less than a half. But now all the points on the x-axis, or equivalently here the y-axis, are within a half of some integer, apart from the ones that are exactly at the midpoint, and the measure of those points now is 0, and so we can forget about that. Right, Hawkeye was right. So Hawkeye gets a gold star, but unfortunately I don't have any. Nor, if I were in class, I would be tossing candy to students, and I would I give people who spot errors 2 candies and people who ask questions 1 candy, but here I really can't do anything, so I will just skip it. Anyhow, so in terms of the function f hat of y, we can rewrite this Fourier series as f hat of y, which is basically f sub n. We then replace n by the integer closest to y, and then we integrate from minus infinity on y, but we do that integration in steps. We do a sum on all integers, and then we integrate from n minus a half to n plus a half. And so we're recreating here exactly this expansion. And on the other hand, this sum and integral is equivalent, again, apart from a measure 0. And you see why Lebesgue integration is relevant in this case, because these steps that I'm doing here, I'm actually dropping a set of measures 0. In any event, we then have rewritten the Fourier series in this way, which already looks like a Fourier transform. And now we send L to infinity, and you see what we've got here is the integer closest to y divided by L. And the difference between the two, between the integer nearest y and y, can't be greater than a half. And so in the exponent, what we've got is, as an error, we've got something like I 2 pi x times 1 over 2L. And as L goes to infinity, that error goes to 0. Equivalently, you can say the difference in absolute value between e to the I 2 pi nearest integer to y x divided by L minus the same expression with y is the same as this, and this is just I mean, if I add in that last factor there, that thing is the absolute value of e to the I pi x over L minus 1. And as you know, the expansion of the exponential for small x, sorry, I need to show you this. The expansion of the exponential for small x is 1 plus I pi x over L plus I pi x over L squared over 2 factorial plus dot 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 plus, and then minus 1, this one here, this is approximately pi x over L in absolute value. And so that's what's said here. And that goes to 0 as L goes to infinity. Maybe I should make this A a little smaller and B, put it maybe here or maybe there. Okay, so we can replace the integer nearest y by y in the limit L going to infinity, and now we've got this expression. So that's basically the Fourier transform formula right there. We just define a variable k equal to 2 pi y over L. In other words, we take this expression here. Here we can make this bigger. So we take this expression here, 2 pi y over L, and we set that equal to k. And then we can and then y is lk over 2 pi. And so when we make those substitutions, this turns into that, which is the same as this. And we can define the Fourier transform as we are led then to define the Fourier transform f tilde as this factor here, square root of L over pi, f hat of lk over 2 pi. And if we do, we then have the formula for the inverse Fourier transform. And so what we've done then is a series of steps, which I think if you read the text carefully and listen to this recording a second time, you can see is just taking this Fourier series and sort of massaging it until it turns into the Fourier transform formula. In other words, we've expressed f of x not as a Fourier series, but now as a Fourier transform. This function f tilde of k is defined this way, and if we then unravel the various definitions that we've had, what we find is that f tilde of k is, first of all, it's this expression here, and f hat is this, so we're down to that, and we then get back an expression that f tilde of k is itself a Fourier transform, and in the limit as L goes to infinity, it looks like this. So we have two Fourier transform relations that are symmetrical. It's kind of a reflection symmetry. The function f of x is an integral from minus infinity to plus infinity on k over root 2 pi, the phase factor e to the I kx, and then some function f tilde of k, which we can call the Fourier transform of f of x. On the other hand, f of x can be thought of as the inverse Fourier transform of f of k, or equivalently, f tilde of k, which is the Fourier transform of f of x, is an integral on x over root 2 pi over the whole real line e to the minus I kx times f of x. So there's this symmetrical relationship between the function, its Fourier transform, and the function is an integral of the Fourier transform. The Fourier transform is an integral of the function. Or the function is well, I don't, the mathematics says it much more clearly than I can say it in English. Now, you might worry as you watch this that we've got two pi's here. Where do you put them? Well, you start from these two relations here, and then you can redefine things as you wish. You can just change what you mean by f tilde, and in that case, you can put the 2 square roots of 2 pi on one side or on the other side. Both are okay. And then you can say, well, what is this phase here? Is it plus or minus? Well, you can choose, whatever you choose here, you get the opposite one there. And frankly, all these formulas occur in the literature, mathematical, physical literature, the engineering literature. There's no fixed, rigid convention. On the other hand, what you've got to keep in mind is, as with Fourier series, you can adopt, when you do each calculation, you can adopt whatever convention you please, but you must not change the convention in the middle of a calculation. So that's what's that's a sure recipe for mistakes. So the safest thing is to say, all right, I'm always going to use this convention. Then you have no problems. But on the other hand, if you want to change the convention, we'll change it, but then stay with what you've changed it to. Don't flip-flop in the middle of a calculation. Now, one sometimes needs to compare a Fourier series for a function with the Fourier transform of a function. For example, one might have the Fourier series and want to know, well, what is the Fourier transform? Can I figure that out? Or one has the Fourier transform and wants to know, well, what is the Fourier series? And to do this, well, you just play with the definitions that I've just written down. So basically, the Fourier series looks like this. And we can then switch from 2 pi nx to knx, and using the definitions that we've made, we get to a Fourier transform. So this compares the Fourier series with the Fourier transform. And if we recall our various definitions, we can say f sub n is f sub integer nearest n, or f sub y, f hat of y, and we get down to this. So the relationship between these Fourier coefficients, the Fourier coefficients are this square root times the Fourier transform. And so that's how you get the Fourier series from the Fourier transform. On the other hand, well, I guess we go to another step here. The Fourier series then looks like this, and we can rewrite it like that. So these are the Fourier transform. This is the Fourier transform evaluated at k sub n. And so if we know the Fourier transform, we know the Fourier series. To go the other way, you recall that f tilde of k is equal to this, which is was defined as that. And so you then say that f of x is the integral of its Fourier transform. And then you replace this by that, and you get this. And so this tells you then that you can get the function as an integral of the Fourier coefficients, but the Fourier coefficients here are defined in terms of the nearest integer function. Normally I skip the examples, but today there are a couple of examples that are so important in physics and engineering that I think I should do them. In fact, they're even important in statistics and biophysics and medicine, although biology and medicine are just incredibly non-mathematical even today. In 2020, I've heard biologists at NIH confuse exponentials with logarithms. And that they don't realize that 2 to the n is an exponential. It's just hopeless. Anyway, so the Fourier transform of a Gaussian is a Gaussian. And so let's take the Fourier transform of a Gaussian. Here the Gaussian is f of x is e to the minus m squared x squared, m being a real number. And so we want to compute this. Now, what's often useful when you get an expression like this, where you've got a variable that you're integrating that occurs in an exponential quadratically and linearly, is you complete the square. So you rewrite this like that. And if you expand this, you can see that you have exactly the same thing. So it turns out, as we'll see when, well, first of all, if ik were actually real, then we would say, oh, we're done. We just change variable, we just shift since the integral is over the whole real x-axis, we could just shift x by adding minus whatever this is, and then we just have e to the minus m squared x squared, and we'd be done. Now, it turns out you can do the same thing in this case, and we'll learn why in section 614 when we are studying analytic functions. And basically, we can replace x by x minus ik over 2m squared. And let me, since we've got this screen over here, let me, let's see, I can erase this. Erase that, move this out of the way, go back to a pen, and say what we're doing. You see, this original integral that we were doing was from minus infinity to plus infinity, or if we want, we can say we're taking the limit of an integral from minus L to L along this way, along the x-axis. And what I'm saying is you can also do the integral along in the complex plane, but somewhat lower, namely the distance here is minus ik over 2m squared. And why is it that this works? Well, it's that in the limit of L going to infinity, we can complete, we can consider what's the integral along these two edges, and that integral turns out to be 0 in this case, because we've got a factor of e to the minus x squared. So this is suppressed by e to the minus m squared, L squared, if we're out here at L. And and then the fact that these two are the same is due to the fact that this is an analytic function of x. And so if we integrate along any complete loop, we get 0. So the integral of an analytic function along a closed loop with no singularities inside the loop is 0. And that's what's behind this trick. Well, we'll learn that later. Anyway, what we get then by adding or subtracting ik over 2m squared, is that this just turns into e to the minus m squared x squared. And this is a well-known integral. And what we get then is this expression here. If there is popular demand, I'd be happy to derive this integral. This was famously derived 100 or 200 or 300 years ago by various famous mathematicians, and there's a very cute proof of this. So if people in the chat want to see it, I'll do it. Otherwise, you can just say, well, we look up an integral table or we use Google or something. So what have we found? We found that the Fourier transform of Gaussian is another Gaussian. And so if we have e to the minus m squared x squared in position space, we have, apart from the prefactor, e to the minus k squared over 4m squared in Fourier space, or if you want, in momentum space. And notice the two Gaussians are so very, very different, because if the Gaussian in position space decreases slowly because m is small, then its Fourier transform decreases rapidly because m is small. And equivalently, if this decreases rapidly because m is big, then its Fourier transform decreases slowly because m is big. And so the behavior of Fourier transforms, in other words, if f of x looks like this, let me get, yeah, all right, f of x looks like this. So let me say, it looks like this. Then f tilde of k looks like this, very smooth. On the other hand, if f of x looks like that, extremely broad, then f tilde of k will be something like that. And the extreme example of this is something that we'll come up with in just a moment when we see that the delta function is an integral e to the I k x dk over, and now I'm going to put a 2 pi there to avoid having a 2 pi there. Anyway, the delta function. So what is this? This delta function is infinitely steep at x equals 0. Its Fourier transform is just the number 1, and it's just infinitely broad. And of course, this is behind, all of this is behind is why we have an uncertainty principle in physics. There are two reasons. One is the nature of the Fourier transform. The other reason is that momentum space and position space are related by Fourier transformation. And that's partly related to the fact that we can identify the momentum in quantum mechanics with the ability to displace in position. And that's behind this representation. All right, so I think I'll end that. So let's see, where was I? Well, here we have the Fourier transform of Gaussian and the Gaussian and so forth. Now, how about going from f tilde to get x, to get f? Well, our standard formulas then are that the function f of x is an integral of its Fourier transform. And if we substitute f tilde of k equal to this in there and complete the square, we get that. Once again, we do this trick of here of how things work in for analytic functions. And we jump from that to this, and now doing this integral, we just get e to the minus m squared x squared. So that's, so what we see is we've taken the function e to the minus m squared x squared, computed its Fourier transform, gotten this expression, then we write the function f of x as the integral of its Fourier transform, and then we wind up with, we get back the function e to the minus m squared x squared, as of course we must. So let's see, do we have some feedback? Does anybody have a question or a complaint or a suggestion? Well, if the function's real, let's remember, if Fourier transforms are real, then there's a certain relation for the coefficients of Fourier coefficients for a real function. If a function's real, then the complex conjugate of its Fourier transform, well, the Fourier transform is given by that. If we complex conjugate it, we get a star here, but the function's real, so there's no change. We go from e to the minus ikx to e to the plus ikx. But this, by definition, is just f tilde and minus k. So for a real function, the complex conjugate of the Fourier transform is the Fourier transform evaluated at negative argument. So the complex conjugate of the Fourier transform at k is the Fourier transform at minus k. And one can derive various cute things from that, which I'm going to skip. Let's now get to, in fact, the delta function business. And what we're going to do is just repeat essentially something that's very much like what we were doing for Fourier series, namely that, by the way, let me just ask the class, I don't immediately remember, did I go over the part of the examples section? Let me just show you which part, because I want to make sure that I actually did this. Did I? Well, yeah, I did that, but did I? Let's see, maybe it's here. Right, did I go over section 3.2 of examples in class? Oh, all right, there was a question. The complex conjugate of a real function is the function itself. So let me somehow get us back to this. So in other words, so let's see, if f is real, well, what does that mean? That's the same thing as saying that f star of x equals f of x. So the complex conjugate of a real function is the function itself. Now, would somebody in class tell me, did I cover section 3.2 in class? I meant to, and I don't know if I did that on Wednesday. So I'll give you a few minutes to think about that. In the meantime, I guess I'll go on with the Fourier transform here and delta functions. And so I'm going to do what we did for Fourier series, namely we write the function as its, in terms of its Fourier transform, then we write the Fourier transform in terms of the function. And when we combine those two things together, The product of exponential, of course, is the exponential of the sum of the arguments. And so we get this expression here. And of course, we compare that with the delta function relation. What we see is that the delta function of x minus y is an integral dk over 2 pi e to the I k x minus y. And if instead we say, well, how do we know this is true? Can we evaluate it numerically? And using MATLAB, I've done that for you. I've taken n to be 10 to the 6th. And if we just do the thing exactly, we get sine n x minus y over pi x minus y. And this, by the way, is a ratio that one sees various times in scattering theory and quantum mechanics. Let's look at figure 4.1. Well, here is the finite Fourier integral for a Dirac delta function. In other words, it's this integral, but from minus a million to plus a million. And we see a spike here that goes up to 350,000, whereas this axis here is 2/1000th. It's hard to say that. And notice the Gibbs overshoots here. And what you can see is that if you integrate a function times this, take any function f of x and integrate, so you form an integral of f of x times this delta of x here, dx. Well, what you're going to get is over here, if the function f of x is more or less continuous, the values of the function are just going to cancel. They're going to cancel almost completely. Here, in the case of integrating from minus a million to plus minus a million to plus a million, but as you change from 1 million to 10 million to 100 million and so forth, this spike goes up, this thing squeezes down, and these oscillations become ever more rapid. And so we just get f of 0. So that's basically that's why that's an illustration of the truth, or that's the sense in which this equation is true. And of course, when, as I said, the delta function is not really a function, it's a functional. And so it means that what that means is that the delta function maps a function f of y into its value at y equal to x, which is over here. But it's a functional that works on a certain space of functions, and the space of functions is functions that are suitably smooth. And what we can see from the graph here is if the function's continuous, then bingo, this formula works like gangbusters. On the other, what mathematicians do when they discuss functionals is they put huge restrictions on the space of functions, f of y, the Russian mathematician Gelfand, for example, liked to use a space of functions that were infinitely differentiable, but were zero outside some finite region. And in fact, those functions are so little used that he, in his book on the subject, he wrote 6 books, I think, on functionals. And in the first chapter of the first book, he had to demonstrate that these functions actually exist, because people wanted to say that, well, if the thing is infinitely differentiable, but it's zero and outside of some finite region, then you just make a Taylor series where the function is zero and you just get it to be zero everywhere. Well, of course, that is assuming certain things about the range of the Taylor series. Anyhow, I think I've gotten carried away there. Let's say a question or an answer to my question would be helpful. Students need to, if students guide me, I'll teach better than if you just let me go my own way, and I'm liable to just sail through intellectual space like a dead rock. Anyway, so let's go back to the formula for the delta function and multiply it by f of y, do the integration. And then, of course, that immediately gives us back the Fourier transform relation. And we can then take the inner product of two, or define the inner product of two functions by this equation. It's the integral of f star of x with g of x. So as usual for an inner product, we complex conjugate the object on the left and not the one on the right. So so this is our definition of the inner product of two functions, and writing them each as Fourier transforms, and then using the delta function relation, what we see is we just get that the inner product is also an inner product of their Fourier transforms. So this is sometimes called Parseval's relation. The inner product of a function f of x with a function g of x is an integral f star of x, g of x over the real line, but that's now the same as the integral of the complex conjugate to the Fourier transform of f times the Fourier transform of k integrated along the k-axis. And so that's interesting. That means that the inner product of two functions in position space is the same thing as their inner product in, I'm calling it momentum space, but it's really wave number space. What that means then is that the Fourier transform is a unitary transformation. That is to say, it preserves inner products. The inner product of f with g is the same as the inner product of f tilde with g tilde. And so that means that the map from f to f tilde is unitary because it preserves inner product. Okay, here, let's see. Is that what is used for signal decomposition? Well, I'm not sure what is used for signal decomposition, but I would imagine that Fourier transforms and Fourier series are used when one wants to do signal decomposition. I've never worked in that area, but typically signals are real, and the signals come in at different frequencies, and we typically want them as functions of time rather than of frequency. Anyway, so let me go on. We have here Parseval's relation, and now if we set f and g equal to the same function, set g equal to f, then the inner product of f with f is, which is an integral of the absolute value of f squared, is the integral of the absolute value of the Fourier transform of f. squared. And so now you see why it is that people, that Fourier transforms are particularly suited to functions that are square integrable. And in fact, square integral in the Lebesgue sense. Okay, so now let me say something that's really important in physics and engineering, namely, what do you do with delta functions that have more complicated arguments? In other words, how do you interpret an integral like this? It's a function f of x, another function g of x, and we have delta of g of x. And so roughly speaking, what this is saying is that, and let's suppose that g is a function that vanishes only at one point, x0, say. In that case, we expect that this is somehow proportional to f at x0, but we don't really know what the factor is. And let's also assume that the derivative of g is not 0 where it vanishes, which is at x0. So the function vanishes at x0, but the derivative doesn't. So that integral then involves f only at x0, so we can pull f of x0 outside the integral like that. And now near x0, we can approximate f as g prime x0 x minus x0. So we can, so j is f of x0 times delta of all those things. And so we can then just multiply and divide by g prime, by the absolute value of the derivative of g at x0. And now what we see is that in here, this thing is g minus g0, and this is dg. And so this is just 1. And so we evaluated the integral. This original integral, we knew it was proportional to f of x0. We weren't sure what the factor is, what the factor was. And now we see the factor is 1 over the derivative of this function evaluated at the point at which the function vanishes. So if the function g has a single value, single 0, and the 0 is at x equal to x0, we have the integral delta of g of x times f of x is f of x0 over the absolute value of g prime of x0. And physicists write this as delta of g of x is delta of x minus x0 divided by the absolute value of g prime at x0. And if g actually has several zeros, so let us say x sub 0 k, then we have to sum over them. And so then what we get is that this integral is sum over the zeros, f evaluated at each 0 of g and divided by the derivative of g at that 0 of g. Or equivalently, it's a sum of delta functions x minus x0k divided by g prime of x0k in absolute value. Now, I guess I'll just abbreviate this. We can go over this more carefully on Wednesday of next week, but the basic rule is that if g is 0 at x0 and its derivative is 0 at x0, and x0 is the only root of g, that is to say x0 is the only place where g vanishes, then delta of g is delta of x minus x0 divided by the double prime, second derivative of g at x0, and absolute value divided by x minus x0. Now, we previously had a Dirac-Combe formula, and if I put my my mouse there, let's see. Unfortunately, this thing tilts it to one side, so we get a lot of useless information, and then we don't get the other hand of the equation. Well, this tells us that the sum of the phase factors here, e to the minus I n x over 2 pi, right, which is this, this is 1 over 2 pi plus 1 over pi times the sum of the cosines is this Dirac-Combe. We multiply it by f of x and integrate over the line, we get this expression. And so on the left-hand side, we have this integrated with f. On the right-hand side, we have the Dirac-Combe integrated with f. And that gives us what's called the Poisson summation formula. So, and so what is this? Well, evaluating this, what we get is just for each L, this integral of the delta function gives us f at 2 pi L, but then we have to sum over all L's. And over here, this is the Fourier transform of f at n. So this is f tilde of n at divided by square root of 2 pi. And so this is its Fourier transform evaluated at various n's, and one can relate that to the Fourier series. And if we do, we then get this expression here. And once again, functions, these formulas make sense for continuous functions that are square integrable on the real line. Okay, so can you walk through equation 446 in more detail? Okay, so let's skip back here. All right, so the first thing we do is we say we're trying to evaluate this integral here. And what we know is that this delta function is a huge spike when g of x vanishes. And so and let's assume that g is a function that has only one zero at x0. In other words, g of x0 is 0, but so what we're assuming there is we're assuming that g of x0 is equal to 0, and g of x is not equal to 0 if x is not equal to x0. So that's what we're assuming about g. And we're also assuming that g has a derivative that's not equal to 0 at x0. And so let me just move this over a bit so you can see it. So since we know that the delta function is a spike at when g vanishes, we know that only this integral contributes only when x is equal to x0. So we can pull out f of x0. Here we're assuming f is continuous. If it's not continuous, we really can't do this. So then we're left with the integral of g of x dx. Well, obviously, this can only involve g. And near x0, g is approximately g prime of x0 times x minus x0. Again, we're here where I'm assuming that x is a well-behaved function, so we can approximate it by a Taylor series. And here the Taylor series is g of x is g of x0 approximately plus x minus x0, g prime of x0, and then plus other terms that we ignore for x when x is close to x0. So we substitute that expansion in here, and we get this. And now we just multiply the integral by the absolute value of g prime of x0, and then divide by the same thing in front, so the thing cancels. And now we look at what we've got. Well, this thing inside is delta of g minus g0. And this thing here is dg. And so what we can say then is that this integral is just an integral. It's now a delta function of g, and it gives you 1 when you integrate over g0. And so this just gives us 1, and we have then f of x0 over the absolute value of g prime of x0. So that's the way I'm thinking of it. The other thing is that delta functions are even functions, so the sign of what's in here doesn't matter. It's just the magnitude, and in fact, it's only you get the spike only when the magnitude is 0. So I hope that was helpful. So we've derived these two formulas, which are called the Poisson summation formula. And as an example, we've seen that the Gaussian f of x has a Fourier transform that looks like that. And so the Poisson summation formula then is that the sum of the Fourier transform variables and the over k is equal to the sum of the function variables evaluated at x equal to L, little l, big L. And that gives us this expression here. And so that means that these two sums are equal. And on the other hand, one sum, if m is large, this sum converges rapidly, and this one slowly. If m is small, this one converges rapidly, that one slowly. So one can choose by using Fourier transform or Fourier series coefficients, which to use, whether it's the function or its transform. One can get either a rapidly convergent sequence or a slowly converging sequence. And there's a technique called Ewald summation that makes use of this. Let's see, we've only got about 6 minutes left, so we've just had a couple of questions. Are there more questions? And no one ever told me, did I cover this did I cover this on Tuesday or Wednesday? Well, since we don't have any statement, I'll go through it again. Suppose we have a set of orthonormal functions, that are orthonormal on an interval from A to B, then these functions will span a certain set, a certain space of functions, a vector space of functions. And each of these functions is an infinite sum of fn, hn of x. In Fourier series, one numbers the functions from minus infinity to plus infinity. Here, I'm just numbering them from 0 to infinity. But one could do either one. The orthonormality, as for Fourier series, the orthonormality of the functions means that fx integrated with the complex conjugate of hn of x gives you the nth coefficient. And these functions are analogous to the functions of the first three functions in the chapter on Fourier series. And if we then do the same thing we did with Fourier series, namely, we write the expansion this way by replacing the coefficients by their values, which are integrals like this, we then get this expression, which tells us then, since f of x is an integral of f of y times this thing in the parentheses, this tells us that the sum in the parentheses is a delta function. And so this is a kind of universal thing, that whenever you have a set of orthonormal functions. Oh, wonderful. Wonder Woman and Fantastic Four Vector have answered my question. Okay, great. Well, I'm glad I guessed at what the answer was. So this is important because you see, it shows you that the Fourier series are just one example of an infinite class of relations. That each of these, in each case, you've got a set of orthonormal functions. You can think of them as vectors in function space. And if you take, so to speak here, a dot product of these functions, you get the Dirac delta function. And on the other hand, you can expand any function in the function space as just a linear combination of these basis functions. As in equation 3.9 of the examples chapter. By the way, there's just one link necessary to get to the videos. The Wednesday videos are all on a UNM webpage, which has just one link. The link takes you to the page, and then you can click on any video you wanna look at. So let's see, there are only a couple of minutes left now. I don't think I should start anything new, but if there's another question, I think I have time to answer one or two questions. I keep thinking of all of this mathematics in terms of quantum mechanics. I don't know whether that's means that I'm focusing too much on quantum mechanics, but there are direct relationships between linear algebra and quantum mechanics, and Fourier series and Fourier transforms in quantum mechanics. And in fact, that's why I put these chapters at the beginning of the book. And the reason being that beginning graduate students need this mathematics so that they can understand quantum mechanics without being confused by the mathematics. In quantum mechanics, you should be confused by the physics. That's bad enough. If you're confused by the mathematics and the physics, then you really are, you're really in trouble. Well, you may not be in trouble, but you're in you need to do a lot of work. Whereas if you know the mathematics, then the physics, you can learn the physics fairly rapidly. So the point is that some of you may be taking quantum mechanics simultaneously with this course, and in that case, doing the Fourier series, Fourier transforms, and linear algebra first, I think, is a help. Later on, the material on analytic functions and differential equations and so forth, that's also relevant to quantum mechanics, but it's also relevant to electrodynamics and mechanics and thermodynamics and so on. All right, well, we're just about out of time, and I don't hear any more questions. So I hope that you all stay healthy. I recovered from what I had was a 24-hour bug. And if you're wondering about my lip, it's that I was in bed looking at something on my iPad, and I dropped the iPad and it fell on my lip. And that's why I have a swollen lip. Anyway, well, I'll put the video on the web on YouTube tonight, and I hope you all, as I said, stay safe, stay healthy. Yes, you can meet the dog, but the dog doesn't listen to me any more than anyone else does. Sam, here he is. Come on, they want to meet you. Come over here. Can you? Come here. Come here. All right, this is the dog. His name is Sam, and he's a very sweet dog, but as I said, he doesn't do much. He doesn't answer me. Doesn't listen to what I say, but he's very sweet. Sometimes he does the right thing, and sometime, if you want to meet Sam, send me an email after we have a vaccine, and I'll bring him to the physics department. You can all play with Sam. He's a very sweet, friendly dog. But if anyone has a cat or a mouse or a skunk or any other small animal nearby, Sam will charge, and unless I've got a firm grip on him, he'll get loose. All right, so I've dragged on. Let me just end this thing now. So let's get up here, stop share. Where is